set all of those work equations equal. P times change in V equals mgh equals force times distance every time. Every time, everything is equal. Same with magnetism, right? When we talked about circular motion, right? If you're in a uniform magnetic field.
Yeah.
Same thing. We have a circle, so we know what the equation is for a circle with acceleration. What is that? Centripetal acceleration equals mv squared over r. We can now set that equal to the magnetic force equation because that's creating the centripetal force. So as long as you recognize it's the same thing, the magnetic force is creating the centripetal force. So we have mv squared over r equals, what is magnetic force? QVB sine of theta. Got it. Yep. So make connections. Draw every connection. That is a very important point you brought up. You want to connect everything together. So if you see kinetic energy, they're all equal. All right, so the whole point of kinetic molecular theory is if we increase the temperature of a gas, what happens to the kinetic energy? Increases, good. Okay, what is diffusion?
Movement of a substance from higher concentration to lower concentration.
Very good, in an open environment, right? As opposed to effusion, what's happening in effusion?
It's a closed environment.
Closed environment, so specifically it's almost like going through a straw. So you have one container attached to another container, and there's a little hole in between them, like a straw. So you just have gas going through the straw, right? Both of these terms, one fundamental, what is this? How does speed relate to molecular?
The smaller the particle, the faster
The smaller the particle, the faster the rate of diffusion or effusion. Yeah, which is just the movement of the molecule. Good. All right, you all have been studying very well. Dalton's law of partial pressures. What is that?
total pressure equals partial quality sum.
Add up all the partial pressures of your gas. Now, partial pressure we like to think of as synonymous with, anybody remember? Something with partial pressure. We think of it as the same thing as
I remember this being in the.
concentration.
Yeah.
Concentration. Think of it as the same thing as concentration. It even goes back to KSP. If we want to think about, or I'm not KSP, just K. If we have a container of gas and we want to calculate K, we can plug in partial pressures instead of concentrations. Okay, so you can use them interchangeably. Partial pressure, concentration, think of them as the same thing. Okay, same thing with rate laws. If we want to calculate the rate law of a gas, you can just plug in partial pressures if they don't give you concentration. Same thing. Okay, just think of them. It's just concentration of a gas. That's all. So the total partial pressure, you just add up the individual partial pressures, right? Okay. So that's like total pressure equals P1 plus P2 plus P3 and so forth. All right. What is a mole fraction?
Basically, how many moles in one molecule versus the atoms?
Divided by
How many
moles of your entire
molecule
solution.
So it's
Yeah.
moles
So it's
of
moles
that
of one
substance.
moles of one substance, whatever they're asking for, divided by moles of everything, including the original substance. That's why we determine moles of solution.
So it's basically like Na over NaCl, like the mole of.
You got it. It'd be like if you're asking what is the mole fraction of sodium in sodium chloride, simply the moles of sodium divided by moles of sodium chloride.
But you would have to be the moles that have dissociated.
Yes. Yeah, whatever end result of sodium you have, that's what you plug in for the numerator. Yep. STP, what do you think?
0 degrees.
0 degrees, what?
Celsius.
Celsius, good. So that's how many Kelvin?
273.
Very good, 273 and
1 atmosphere.
1 atmosphere of pressure. Good. Let's see. Standard conditions.
25 and 298.
25 degrees Celsius or 298 Kelvin and how many pressures of?
1 atmosphere.
Same 1 atmosphere is good. Okay. So this is important. Know the distinction very well because they can test. They love to test the difference.
298 for standard conditions.
If you see something like this, what does this mean?
Enthalpy.
This is the change in enthalpy that occurs in a reaction at standard conditions. If you see a little degree sign, you gotta think standard
So
conditions.
it's 298, 1 ATM, and what?
298 Kelvin and 1 ATM. That's it.
STP is 0 degrees C.
273 and 1 atmosphere.
Yep. All right, know that one. Know the difference quickly. All right. Liquids. What can you all tell me about liquids?
Usually polar covalent bond.
Usually polar covalent. Good. What else? Other properties. They fit the size of the container. They have more kinetic energy than solids, but less kinetic energy than gases. They're moving around, but they're still attracted to each other. Okay, they fit the container. What is miscibility?
How well something mixes.
Miscibility. All right. What is it?
How well things mix.
How well things mix together. Okay, so I just like to think of what's the rule for solubility?
Like this one.
Like dissolves like. So if you have two polar substances, are they more miscible or less miscible?
More miscible.
More miscible. Good. What about CH3 mixed with some ethane?
Not miscible. Oh, actually, that's what miscible.
Ethane?
Those are miscible, yeah,
Yeah.
because you have
Two non-polar.
two nonpolar. Exactly. Like dissolves like. Very good. What about immiscible? Give me an what is immiscible?
Like oil and
Polar and
water.
non-polar.
Polar and nonpolar. An example is
Fats and water.
fats and water, oil and water. Very good. What is an emulsion?
Polar and non-polar substances together.
Yeah, exactly. It's just a polar and a nonpolar solution or mixed together. We shake it up. If we shake it up, it looks like it's mixed.
And then it'll
That's your
settle.
emulsion. Then if we let it sit together, it's going to settle into those two layers like we saw last time with Orgo, right? Which layer is on the bottom? Which one's on the top?
The heavier layers on the bottom.
Inorganic
Which one?
layers.
Aqueous layers.
Aqueous layer is on the
Bottom.
bottom. Good. Why?
Because
More
it's-
dense.
More dense. Why?
More intimate forces.
There you go. More molecular forces bringing it together. Less volume, thus greater density. Good.
What's on the top is the organic layer.
Organic. Yeah. Yeah. So again, it's just like centrifugation. The most dense stuff goes to the bottom.
The organic layer usually like refers to.
Organic is the top layer, so that's a lot of nonpolar stuff.
Alright,
All the nonpolar stuff, yeah. All right, that's your emulsion. Okay, solids. What do we know about solids?
Ionic bonding.
Ionic
dipole.
bonding, good.
Very low.
Ion
entropy.
dipole, good.
Very low entropy.
Very low entropy. Oh, I forgot about that one. Entropy. So again, I didn't make the connection to entropy, but if I'm tested on entropy after dealing with all this stuff, he's going to get to the answer quicker than me. This is why we got to make as many connections as we could possibly make. Very good. Entropy is the least for solids. What about for gas?
Highest.
Highest entropy for gas. Good. Okay. So solids have lower entropy. What else? They do not fit the size of their container. They're stationary. Okay. What do we know about the atoms as they sit there stationary? Typically held together by it could be ionic bonds, but they're still shaking. All the
Or
energy.
vibrational energy.
Vibrational energy. So before, as a liquid, you had some kinetic energy, or as a gas, you had kinetic energy. All that energy has been converted. Now it's just the molecules are sitting, they're stationary, but they're still vibrating. Okay, there's still movement in those particles. They're still vibrating. Solids. And then I would kind of, if I'm tested on solids, I would start thinking of some other concepts that relate to solids. What other concepts have we talked about that relate to solids? I would think of the moduli,
Oh, the physics model.
the physics modulus, yeah. Young's modulus, bulk modulus, because those are all dealing with solids. Remember, pressure, F over A, it's stress over strain. Pressure divided by change in volume. You guys remember that?
Force over the area divided by.
Strain, which is kind of the change of the
Change of
volume
length
or change of the length. It depends which moduli you're looking at. But again, those deal with solids. So
Yeah, I don't know.
yeah. So again, now we're just starting to connect Gen Chem and physics. That's what we're starting to do. Okay. All right. Temperature change during a phase change. First of all, what is a phase change?
Where it changes states from like solid to liquid.
Good. What is the temperature change at that phase change?
There's no temperature change.
No temperature change. So if we ask what is the change in heat, or how much heat was absorbed by the system?
Q equals.
Q equals ml. Very good. Now, if the phase change occurs as we go from a solid to a liquid, what type of phase change?
It melting.
Solid to liquid is melting, also known as
Fusion.
fusion. Okay. So if you're ever asked to calculate Q equals ml, what is that L going to be called? Heat of
Fusion.
fusion. They're not going to say heat of melting. They're going to say heat of fusion. That's why you have to learn these secondary words. Does that make sense?
Yeah.
All right. What about freezing? What is freezing?
Condensation.
It's the reverse. It's liquid to solid. Good.
What's
What
condensation?
No, that's crystallization.
Oh, sorry.
Condensation is
condensation?
gas to a liquid.
Gas to a liquid. Yeah. So the other word of freezing, if you have to calculate Q equals ml, crystallization. Heat of crystallization. Good. What is evaporation?
So crystallization from
Liquid to
liquid to
gas.
solid?
Same thing as freezing, so what is freezing? You put a cup of water, liquid to solid, yep. Evaporation is from
Liquid to gas?
liquid to gas, good, also known as
Heat of vaporization.
heat of vaporization. That's the L in Q equals ML, very good. Condensation,
Gas to liquid.
gas to liquid, good. Sublimation,
Gas to
Solid to gas.
solid directly into gas, good. Now where is that on your phase diagram?
At very low
Temperature.
temperatures.
At the very bottom, right? So if you have your phase diagram, this is pressure, temperature. Okay, if anything other than water, what is the phase diagram going to look like?
It rolls out instead of.
This is everything other than water, right? What about water?
The middle line curves to the.
Yeah, if it was water, this middle line, this is just water, middle line will curve to the left, right? I'm going to write H2O here. Okay. So any phase diagram, actually you guys show me, where is evaporation? So evaporation's
There's
go,
solid, liquid, gas.
yeah, so everyone remember, start off,
It would be
one
like-
way to remember which way to start is, what happens if we have really far to the right, we have a really high temperature, so obviously we have a
Gas.
gas. So that's how I remember it. Gas is all the way on the right, then liquid, and then solid. Okay? So where is evaporation?
It's somewhere between liquid.
We start somewhere here, and how can we go to a gas? With
Raise
two-
the temperature.
we can raise the temperature, or
Lower the pressure.
we can lower the pressure. Yeah. Or we can do both. Yeah, good. All right, where is sublimation occurring?
Gas.
That's low
Solid
pressures
to
and low
gas.
temperatures.
S for solid, sublimation, we have to have low pressure. We have to be in the very bottom because otherwise we're going to cross into liquid. Low
It has to be
pressure.
at low temperatures to do that.
Yeah, and low temperatures, yeah. You have to start somewhere in this area. All right, what is deposition?
Gas to solid.
Gas to solid. So this is kind of depositing or forming those solids, the reverse of sublimation. Good. All right, what is vapor pressure?
It's the pressure that forms over a liquid as like it starts to heat up, right?
Or naturally, every solution will have some...
Like a can of Coke.
Yeah, like a can of Coke. Every solution will have some molecules that, a little bit different than that. Every solution will have some molecules that break the intermolecular forces and escape as gas. But it's just a little bit, okay? So the whole point is if we start heating up our liquid, we're breaking more and more of those intermolecular forces, more and more molecules are building up above the solution. But they're kept right above that solution container. Why are they kept right above the solution?
Air pressure.
So here's the liquid. Now, there's just going to be some vapors. Even as we heat this up, there's still going to be a buildup of vapor, but it's going to sit there. Why does it only sit there?
Because of atmospheric pressure.
Because of atmospheric pressure. Exactly. Atmospheric pressure is sitting at, what is atmospheric pressure?
1 ATM.
1 atm, good. So as we're building up this pressure, it's going to sit there until when? Until
Exceeds the
until vapor pressure exceeds 1 atm, good. Then it's going to escape. It's just balancing out of forces. That's all it is.
So is that all boiling point is? It's just when
All boiling point
vapor
is
pressure exceeds.
vapor pressure exceeds. Yeah, really, the exact boiling point is actually the point where vapor pressure equals atmospheric pressure. Then, as we keep adding more heat, then everything escapes. So 100 degrees Celsius for water is the point when vapor pressure equals
Okay.
atmospheric pressure. Yep. All right, where's the triple point on that phase diagram?
It's where all meet, so it's like right.
It's where they all meet, and what does that tell us?
That's a critical point.
And what does that mean? It means our molecule or solution is a little bit, it's every one of those phases, all phases. We really can't determine one phase from the other.
Just
Okay?
like a hybrid columns.
Yep.
So what's the critical point again?
Critical point is either this top one or this top one.
Okay.
It's basically beyond the critical point, we don't really know what the phase of the molecule is. It's kind of a mixture between liquids and gases. Okay? So if we go above any of these critical points to the right or above, we just don't know what the exact state is. Okay? Now what if we are on a line? What if we are right here? What does this tell us? What is the phase? Or just tell me what's going on there.
Is it in a phase change?
Fusion.
It's at a phase change. Okay, if we cross it as a phase change, but what if the molecule is just sitting there? What if it's set there and we don't change anything?
Is it gonna stay in its state that it was in?
It's actually, this is known as a phase equilibrium. We're basically at an equilibrium between the solid and the liquid. That's all.
What is that, what did you say?
If we're on a line,
Oh, yeah.
that's called a phase equilibrium. We're just kind of in between the solid and liquid phase. Okay? But if we add heat and we raise the temperature, then we become becomes a what?
If you added heat, it would go to gas.
If we're right here?
Oh, right there, you go to liquid.
Liquid, good.
Are you recording all this?
What's up?
Are you recording all this?
Yep.
Oh, cool.
Yep. All right. Phase diagram of water. Now, can someone explain to me, I know we talked about this, why is the phase diagram of water bent to the left?
Because it doesn't follow the same rules.
Doesn't follow the same rules. What is the difference between water and everything else?
Hydrogen.
Hydrogen bonding, which does what when it changes into a solid versus a liquid?
It makes it's less dense as a solid.
It's less dense as a solid because hydrogen bonding doesn't work there.
Is it because of the intermolecular forces?
Well, it's because hydrogen bonding, you need those molecules to line up, right? For hydrogen bonding to occur, we need one of these. So in this case, oxygen for water. You need the oxygen bond with the hydrogen. You need this to surround. You need these molecules to align. They have to move, exactly. They have to move and align so the hydrogen of another molecule aligns. Same thing, surrounding the oxygen. Literally surrounding that oxygen, because it's such a large atom compared to the hydrogen, that oxygen is going to be surrounded by multitudes and many, many hydrogens of other molecules. Okay? But for them to move around, it has to be liquid phase. As a solid phase, you can't get that movement.
So it's not a
So there's no intermolecular, there's less intermolecular forces, so the whole, goes back to our rules. The less intermolecular forces, then the less boiling point, the less melting point, the less density. Yeah. And because it's less density, that's where this stuff applies. So the whole point is, if we start off as a liquid, so in this case, this is liquid, right? This is solid, I should have made that clear, right?
Yeah.
If we start off as a liquid, and let's say what did we say with the with less hydrogen bonding, we decrease. So I like to just, another way you can figure this out is think of the polar ice caps. Ice is just floating on top, meaning it's less dense. So less dense means less pressure. Pressure and density is almost the same thing, right? Higher pressure means it's more dense. Right? Everyone understand that? So the whole reason it's different is because of hydrogen bonding. You only get that in the liquid form. And hydrogen bonding is so strong that it makes it more dense as a liquid. Okay, but only with water. We don't care about anything else. Everything else, use the original, everything to the right. Use the original phase diagram. All right, any questions? What is a colloid?
Oh,
It's like,
So where
it looks
the,
like it's suspended, or it looks like it's.
okay, so it's just a solute in a different phase from the solvent. That's the basic way to think about it. So an example is foam. What is foam?
It's
So
a.
just look at foam, imagine foam, what does it look like? It looks like a bunch of, what does shaving foam look like? It looks like
Bubbles.
lots of bubbles, so that's a gas. Probably, so if you think about what is a solute and what is a solvent, solute is the minority product, or minority, solvent is the major or the majority. So if you're looking at foam, what do we see? We see bubbles, but most of it is actually liquid, yeah. So liquid solvent with gas solute. Yep. So just imagine it if you need help remembering it. And what about aerosol? You spray it out of a can, what does it look like? Most of it is
Yeah.
gas, yeah. But then there might be some liquid, or sometimes you can even get solid solute particles. Yeah. So that's aerosol. Typically liquid solute particles. Okay. And again, that's why when you shake a bottle of aerosol, that's why it sounds like there's liquid inside. Because there is some liquid, but the majority of it is gas. All right. Question: if we there's too much stuff up here. I gotta erase it. Okay. If we have 2 molar NaCl in a jar or in a beaker. And then in a separate beaker, we have 2 molar CaCl2. Which one of these has a higher boiling point?
The second one,
This one. Why?
because there's more of it.
There's more ions that will form. Okay, this goes to colligative properties. The more solute particles, the higher the boiling point. Okay, which one has a higher melting point
Higher melting.
or freezing point?
The higher or the lower?
The second.
Higher. Which one has the higher?
I think it's the second one, yeah.
Higher or lower?
Higher.
Okay, there's the first one.
First one.
Oh, because it's ion bonding?
Nope, because there's less solute particles. So this is colligative properties. What's the graph we always think of?
The little like.
Just a V.
Going up and
Yep, just a V. So this is,
curves that show straight.
oh, this is temperature. This is solute particles. Concentration of solute. Really just think of it the number of solute particles. So the top one goes up, bottom one goes down. It's just shaped like a V. Okay, so the top one is which point?
One,
Boiling point. The bottom one is
freezing.
freezing point or melting point, same thing. So remember that. So we said which one has a higher boiling point? Well, it's this one because we have more solute. So more solute, it raises up higher. Okay. Which one has the smaller? Which one has the higher freezing point? Well, it's this one because the more solute we have, the lower it gets. Okay. So just
Yeah.
Yeah,
That just always confuses me, like when you use the terminology in freezing point.
they can give you these types of
So you
questions.
said
You just all you have to do is draw this out.
So
Just draw it out.
So the first one has a lower freezing point?
First one has a greater freezing point, okay? Because think about it. Here we have 2 solute particles. Here we have 3. So the whole point is this has more solute. We're going farther. Freezing point is less for this one. Make sense?
When we say like, because that's what confuses me about it, is like you have to think of it as a freezing point. It's getting lower and lower and lower, so it's greater in terms of freezing point. But
No. Greater freezing point still means higher. Greater freezing point means, think about it. The freezing point was
the
30.
intensity of the freezing point is what I'm trying to say. Like that's what confuses me about it. I have to like read
Don't
it
think
out.
intensity. Just think higher or lower. Make it simple. Don't make
So
it
the
hard.
first NaCl would have a higher freezing point.
NaCl will have a higher freezing point, exactly. CaCl2 will have a higher boiling point, exactly. Yeah. All right. And then osmotic pressure. What's the typical example of osmotic pressure?
It's like the tube with the.
It's the U-shaped tube, right? Okay, we fill up the U-shaped tube. We have a semi-permeable membrane in the middle, right? Fill it up with water, and then we put solute particles in one side, right? So what happens to the water levels?
They even out.
Water will actually move to the left to neutralize or dilute the solute, so water level raises up, this side goes down. But eventually it stops moving to the left. Why does it stop moving? Because there's a balancing force.
There's equilibrium between the water and
Equilibrium.
solid.
Basically, we can't have all the water go to the left. That would form a vacuum on the right. So something has to push the water back to the right. What's pushing it to the right is known as osmotic pressure. Okay? And if you want to calculate the osmotic pressure, the difference in water level, okay, so osmotic pressure equals MRT. So MRT, M molarity, R gas constant, T is temperature. Sometimes they'll give you another form of this equation, and that's why I'm labeling this height. If they ever give you height, it's literally just the difference in height. They have to explain it to you in a passage, but just keep that in mind.
So it would just be like the final height minus the initial height.
But yeah, exactly. Basically, the greater this difference is, the higher your osmotic pressure is. That's the fundamental to take from there. Okay? How are we doing on time?
It's 9:30.
9:30? Okay.
You just want to get through the end of this page. We've only got like 3 terms left.
Yeah, okay. Isolated system. What is isolated system?
No energy, no molecules and no heat can be exchanged.
Good. No energy can change, as well as no molecules or matter can exit or enter. Good. What about a closed system?
Energy can, or like heat can enter and exit.
Heat
but
can enter,
Molecules can't.
Very good. Molecules cannot. They have to stay, but heat can enter and exit. Good. And an open system?
Impermeable
Both.
membrane, so both
Good. So both can enter and exit. Good. And then
So we're
finally,
talking about heat and molecule, right? For isolated, both can't leave, right?
Yeah.
heat or energy.
You can't move in or out.
You can't move, exactly. Very good. And then heat, if you're ever, what is some fundamentals of heat? What do we think of?
Friction.
Okay, friction creates heat. I like to think of Q.
Oh, okay.
When you use Q equals MC times change in T, that's measuring heat. Or Q equals ML, that's measuring heat at a phase change. I also like to think of enthalpy. That's the kind of a heat change that occurs in a reaction. And the real important thing I think of, if Q or change in H is negative, what does that tell us?
Q H is negative.
Q or change in H is negative, so Q
Oh, that means it's exothermic.
or change in H is negative, it's exothermic. What does that mean? It means we
Spontaneous.
we
We gave off.
we
let
release
off
energy. Good. So what's going to happen to the temperature of your solution in an exothermic reaction?
It's gonna increase.
It's going to rise. Exactly. It's going to get hotter. Okay. And then the opposites, Q equal or change in H equals positive. What's going on?
Heat goes into the system.
Heat goes into the system, so it's known as what type of reaction?
Endothermic.
Endothermic reaction. And what happens to the temperature of our solution?
Decreases.
Decreases. Good. Good. All right. Any questions?